So 5.1, extrema on an interval. So these are maximum and minimum values. So here we have the definition of extrema. So that's just our maximum and minimums. At first, we're going to talk about the absolute max and the absolute mins of our graph or of our function. That is the highest point and the lowest point of our graph or of our function. So sometimes our graph may not have an absolute max or min. So looking at A, the highest point of our graph is the point up here. This would be our maximum, our absolute maximum. The lowest point would be down here. This is our absolute minimum. However, if we had an open circle or if it was an open interval, this is not a maximum. So our graph here does not have a maximum value. Our minimum would still be that 0, 1. You're looking for the highest and the lowest y value for your graph. But it has to be continuous and on a closed interval. Next, we're going to talk about our relative extrema. So our relative max and relative min. Our relative maximum would be at the point 0, 0 here. Relative maximum is where we have a hill. So if you have your graph is increasing and then it goes to decreasing where you have that hill, that is a maximum. Our relative minimum would be at a valley down here. So our relative minimum is at the point 2, -4. So where our graph goes from decreasing to increasing. It's not the absolute lowest point on our graph because we have values that are lower over here. But where we go from decreasing to increasing, where we have that valley is our relative minimum, or our relative maximum is where we have a hill. So it's a little bit different than absolute maximum. So for a continuous function, you can think of a relative maximum as occurring on a hill on the graph and a relative minimum as occurring in a valley of the graph. Such a hill and valley can occur in two ways. The first way is if the hill or the valley is smooth and rounded, the graph has a horizontal tangent line at the high point. So horizontal tangent line at the high point or low point. So if we had a hill, our tangent line would be horizontal to that. And then if the hill or the valley is sharp and peaked, so if we had something like an absolute value graph where it's a sharp turn, the graph represents a function that is not differentiable at the high point. So at this point, or the low point, this point would be not differentiable, but that would still be a relative minimum. I just want to highlight a couple of things here. So our graph at a relative max or min will either have a horizontal tangent line at the hill or at the valley, or it's going to be not differentiable at the hill or at the valley. We'll talk about this over and over again on the next couple of slides, but just wanted to highlight it here. Next page, we just kind of have the formal definition of our relative max and mins, but just think about your relative max and mins as a hill or valley. So looking at example 1, find the value of the derivative at each relative extremum shown in 5.3. So here we have our relative maximum. That's where our graph goes from increasing to decreasing. It's this point here. It's asking us to find the value of the derivative at that point. So let's find our derivative of our function here. So f prime of x. How would we find the derivative? What do we do? Awesome. Low d high minus high d low over low squared. Just to simplify it a little bit, I'm going to distribute the 9 to the top up there. So it'd be 9x squared minus 27 over x cubed. So low would be x cubed. What's the derivative of our numerator? 18x, perfect, minus high, which is 9x squared minus 27, times the derivative of our denominator. What's the derivative of the denominator? 3x squared. Over loaf squared, so x to the third power squared. We can simplify this. X cubed times 18x would be 18x to the fourth power. Here I'm going to distribute the x squared, the 3x squared, and distribute the negative. So this would be negative 27x to the fourth power, plus 27 times 3 would be 81x squared. Over, what's x cubed squared? What do we do when we have a power raised to a power? Multiply. So this would be x to the sixth power. We can simplify some more. 18x to the fourth power minus 27x to the fourth power would be negative 9x to the fourth power plus 81x squared over x to the 6. Can we simplify it anymore? We can take out an x squared on top. What else can we take out? I'll take out a negative 9x squared. Then we're left with x squared minus 9 over x to the 6. Can we simplify anymore? X squared, we can take out 2 from the top and 2 from the bottom, so we'd be left with x to the fourth power on the bottom. So negative 9x squared minus 9 times x to the fourth power. Now it asks us to find the value of the derivative at each relative extremum. So we're going to take 3 and plug it into our x's. So we have negative 9 times 3 squared minus 9 over 3 to the fourth power. Three squared would be 9. 9 minus 9 is 0. So we have negative 9 times 0 over 3 to the fourth power is 81. What do we get? What's negative 9 times 0? 0 over 81, which is 0. It gave us the answer here, but that's how we would find it. So what would our slope of our tangent line be? At our point here, at 3, 2, our tangent line would have a slope of what? 0, which makes it a horizontal tangent line. At relative max or minimums, if it is a smooth curve, so what I highlighted on the slide a couple pages ago, if it's a smooth curve, our tangent line is going to have a slope of 0. So it'll have a horizontal tangent line. If it's a sharp turn, like B, let's talk about what our derivative would be here. We don't know how to find the derivative of an absolute value yet, but if we talked about the slope of our line from negative 3 to 0, what would our slope be here? From negative 3 to 0. What's our slope? Negative 1. So our slope would be negative 1. From 0 to 3, what would our slope be? What's our slope? Positive 1. Perfect. So our graph of our slope would look like this. If I plugged in 0, what would our derivative at 0 be? Does not exist, because our graph approaches 2 different values at 0. So when we have a sharp turn, our derivative at that point is undefined. So it tells us here f prime of 0 does not exist when it's a sharp turn, our derivative is undefined. So it says, note that in example 1, at each relative extremum, the derivative either is 0 or does not exist. The x values at these special points are called critical numbers. We're going to use our critical numbers to help us find our absolute max and absolute mins. But relative max and mins either occur where your derivative equals 0 or where your derivative does not exist. So critical numbers only happen when your derivative equals 0 or your derivative does not exist. So on the next page, it says the same thing. If the derivative equals 0, or if it's not differentiable at that number, so if our derivative does not exist, then that value is a critical number. Relative extrema, so relative max or mins, occur only at critical numbers. So we're going to use our critical numbers to help us find maximum and minimums. So it's not going to give us the graph. We're not going to be able to see where we have that curve or a sharp turn. We're going to use our critical numbers to help us. So here we have guidelines for finding extrema on a closed interval. So we want to find the critical numbers. So our critical numbers are either where our derivative equals 0, or where our derivative does not exist, or where it's undefined. Then we want to evaluate what our y value would be at each critical number and evaluate at our endpoints. The least of these values is the minimum, the greatest is the maximum. So this is what we're going to do. We're going to follow these guidelines to find our extrema, or find our maximum and minimums. It'll make more sense after you see it in the first example. All right, so example 2. We want to find the extrema on the interval from -1 to 2. So step 1, let's find our derivative. What would our derivative be of 3x to the 4th power? 12x cubed. What's our derivative of -4x cubed? It's minus 12x squared. Perfect. Now in step 2, we want to find where our derivative equals 0 and where it's undefined. So let's start by finding where our derivative equals 0. 12x cubed minus 12x squared equals 0. What would we do to solve for x here? Awesome, we can take out a 12x squared. When we take out a 12x squared, what are we left with? X minus 1, perfect. So we can set each of these equal to 0. 12x squared equals 0, and x minus 1 equals 0. What does x equal? 0 and 1. Perfect. These are our critical numbers. Do we have any values where our derivative would be undefined here? Is there any value that we would plug into x that would make this undefined? No. So we only have 2 critical numbers. Make sure you check both, but if it's just a polynomial like this, you won't have anywhere where it's undefined. So our critical numbers and our endpoints are where we could have our possible extrema. So I'm going to make a chart. I'm going to put my x values on top and then my y values on the bottom. So our x values, I'm just going to list them in order from smallest to largest, but you can put them in whatever order you want. So -1, 0, 1, and 2. Where -1 and 2 are our endpoints. Zero and 1 were our critical numbers. Now we want to find the y value at each one of these values. Whatever our smallest y value is, that's going to be our minimum. Whatever our largest y value is, that's our maximum. Diego. The endpoint. So let's plug in. We're going to find f of -1. Now we're plugging it in to the original function. We want to find the y value of our original function, not the derivative. So when we plug that in, we have 3 times -1 to the 4th power minus 4 times -1 cubed. So this would be 3 times +1 minus -1 cubed would be -1. So 4 times -1. So 3 plus 4 is 7. Next, let's find f of 0. So 3 times 0 to the 4th power minus 4 times 0 cubed. 0 minus 0, which is 0. The original function here. Next, let's find f of 1. So 3 times 1 to the 4th power minus 4 times 1 cubed. This would be 3 minus 4, which would be -1. And then lastly, let's find f of 2. So 3 times 2 to the 4th power minus 4 times 2 cubed. 2 to the 4th power would be 16, and 3 times 16 is 48. 2 cubed is 8, and 4 times 8 would be 32. 48 minus 32 would be 16. Out of the y values that we have here, what's our smallest y value? -1. So at the point 1 comma -1, that is our minimum. What's our largest y value that we have? 16. So at the point 2 comma 16, that is our maximum. Let's find the derivative. We want to find our critical numbers, so we want to find the derivative first. So our derivative of 2x would just be 2. What's the derivative of -3x to the 2/3 power? Awesome, 2x to the power of -1/3. When we multiply, -3 times 2/3 would be -2, and then when we subtract 1, it'd be -1/3. Perfect. Step 2, we want to find our critical numbers. So we want to find where this equals 0, our x values where it equals 0, and where it's undefined. So let's start by setting equal to 0 and solving. So I can subtract 2 to move it to the other side. So we get -2x to the -1/3 power is equal to -2. What can we do next? What could we do next? Awesome, divide by -2. So x to the power of -1/3 is equal to 1. If you want to change your exponent, if you don't like negative exponents, we can change it. It would be 1 over x to the 1/3 power. Or if you don't like fractions as your exponent, you can change it to be a radical. Either way is equal to 1. If you changed it to be a fraction, you can multiply both sides. So you end up with x to the 1/3 equals 1. How do I get rid of that 1/3 from the exponent? What's the reciprocal of 1/3? I'm going to cube both sides. So we raise both sides to the reciprocal, which would be taking it to the 3rd power. So x is equal to, what's 1 to the 3rd power? 1. So this is one of our critical numbers. Sometimes you could have one critical number, you could have 2, you could have 3, you could have as many as possible, I guess. We also want to figure out where this is undefined. So we want to find where 2 minus 2x to the negative 1/3 power is undefined. Well, let's change this to be a fraction. 2 minus 2 over x to the 1/3. What would make this undefined? If x is 0, yes, if we have 0 in the denominator. So if you have a fraction, set your denominator to be 0 and solve. Here, when we cube both sides, we just get x equals 0. So 0 is also one of our critical numbers. So we're going to do the same thing that we did in the last question. Let's make a little chart. In our chart, we're going to have our critical numbers, 0, 1. What else are we going to have in our chart? Awesome. Our endpoints and our critical numbers are where we could have our possible extrema. So -1. You only have to put these. So only your critical numbers and your endpoints. So let's find our y values. Let's figure out what's what. So we're going to plug in -1 into our original function here. So we're plugging it into this. So we have 2 times -1 minus 3 times -1 to the power of 2/3. So 2 times -1 would be -2. -1 to the 2/3 power is like saying the cubed root of -1 squared. What's the cubed root of -1? And -1 squared? 1. Perfect. So this would be -3 times 1, which would just be -3. -2 minus 3, -5. Let's plug in 0. F of 0. So we're plugging it into the original function. 2 times 0 minus 3 times 0 to the 2/3 power would be 0 minus 0, which is 0. Let's plug in 1. 2 times 1 minus 3 times 1 to the 2/3 power would be 2 minus 3, which is -1. Next, let's plug in 3. 2 times 3 minus 3 times 3 to the 2/3 power. Here you can plug it into the calculator. On WebAssign, there's some questions that your critical numbers end up being a square root. You can just leave it as a square root or leave it as a fraction here just so we can tell what's our critical number and what's not. Plug it into the calculator. We get -0.24, I think. Yeah, -0.24. So let's find our extrema. What is our lowest, our smallest y value? -5. So we would have a minimum at the point -1, -5. What is our largest y value? Awesome. So we would have a maximum at 0, 0. So this would be our answer.